Nice to meet you all. So, our announcer has really knows the lingo. It is pronounced as OPPAV. And for the next 20 minutes or so, I'd like to focus on OPPAV, Technology Demonstrator Program. So this is what I'm going to cover during my presentation. So starting from the program summary, organization chart, development schedule, and the development status, and some results. So this is called the OPPAV Technology Demonstrator Program. This is the official English name for the program. This is the technology demonstration program. This is a demo. Please take a note that this is a demonstrator program. So the OPPAV refers to optionally piloted personal air vehicle. So it means that the OPPAV can go either way. It can have pilot on board, or it can also remotely piloted like UAV. That is why we are calling this demonstrator as OPPAV. So this OPPAV, actually it was originally a generic term, but these days it is it is considered as the same as the eVTOL demonstrator that is being developed by KARI. So it concerns the two key technologies is the distributed propulsion system and the autonomous operation. So we need to have these two advanced technologies, and we need to take those two key technologies viable for this demonstrator to make this program successful. And we also consider the certification process and related methods, and also operation. The goals of the MOLIT covers the certification basis and preparing the draft for that, and compliance check and verification. So to tell you more details, so first let us look at the system specification and primary item development specification, or SS or PIDS. These are some of the things that are carried out by MOTI, or the Ministry of Trade, Industry and Energy. And as I've said, OPPAV can be remotely piloted. So that is why we are also focused on those things. And also, in relation to that, there's a research program by MOLIT about certification, and there's also compliance check and verification. So when we are developing prototype, we carry out compliance checks and verification. And also, our ultimate goal is for the MOLIT is to develop draft for airworthiness standards. So we need to have this airworthiness standard at the same level as for the previous aerial vehicles. And also, we have flight transportation service model that is taken care of by KOTI. These are some of the tests that are conducted by MOLIT. And this is the overall organization chart of the program. So there's KARI, which is Korea Aerospace Research Institute, that is a leading organization on the MOLIT. And KARI is collaborating with industry leaders such as Hanwha. And also in the on your right, there's also KARI, which is a leading organization on the MOTI. It is working with KAI, or the Korea Aerospace industry, and also it is also in developing hardware and software. It is working with Hanwha System, Qtensec, and real-time wave. And also the second project is conducted by KIAST, which is us. We are working with Konkuk University, and this project is about safety verification and safe operation. And fourth project is KOTI, or the Korea Transportation Institute. Their project is focused on transportation service model. So as you can see, there are 4 different projects on the MOLIT. As you can see at the bottom of this slide, all related stakeholders are closely cooperating with each other to carry out their tasks. So let's look at the development schedule. So UAM is a new type of aerial vehicle. So compared to UAV, OPPAV can be developed a little faster. So we have started this OPPAV program back in 2019, and we have carried out SRR, which is a system requirement review, and SER, which is a system design review, in the same year, which was 2019. And in 2020, we have completed our PDR, the preliminary design review. And in March last year, we have completed the critical design review. And this year, we are in the process of developing the prototype. And around June this year, we will do the TRR, which is a test readiness review. And around September, we will conduct FFRR. And if earlier, around October this year, we will be able to have our first flight. So by 2023, we will conduct a sufficient amount of tests for OPPAV demonstrations. So that's our goal. At the bottom of the slide, you will see some letters in yellow. So starting early 2020, in order to improve software system, we have integrated our Subscale prototype, and we were able to successfully conduct Subscale first flight for the Subscale model in November 2020. And in the first, we plan to have our full-scale test demonstrator first flight starting from the first quarter of 2022, and our goal is to complete everything by December 2023. So these are some of the documents that we have prepared for our PDR. So the letters are a little hard to read, but so it shows each different item and how the MOC and how we can carry out MOCs. And this PDR is about 150 pages long. And in the middle, you will see that the loading condition and its analysis. And at the center, you can see the avionics architecture. And this is a fly-by-wire system. So it shows the architecture is really important, and redundancy is important. Architecture is important because it needs to take care of both high voltage and low voltage. And since this is a PDR document, we need to include CFT analysis for hover download. And we have verified the load and weight. And we also carry out the wind tunnel test for aerodynamics. And also, and I'm going to talk about type certification in the later slides. Here, we have carried out all the calculations using the coefficient for our wind tunnel test. And these coefficients will play an important role for the smooth transition flight. So, this is some of the results of the OPPAV test technology demonstrator prototype. So as you can see, these are how it looks. So you can see the front four propellers, tilt prop, and the back propeller, lift prop, and in cruise mode, it will stop. If you can see the wings, it is high wing. It is attached on top. So, the full scale, if we can make this full scale, the wingspan will be 7. And the maximum speed will be 240 kilometers per hour, and the range will be 60 kilometers. And the benefit for this OPPAV test demonstrator, it will be very easy to make it into a full-scale model. So in the future, we can have 5 seats. OPPAV in the future. So at the moment, we are using the lithium-ion battery that is used for eVolt. We will be able to fly from Seoul to Daejeon much faster than the rapid railway. So some of the attributes of the OPPAV TD is that we are using the tilt prop and thrust. We will be able to maximize thrust efficiency. And regarding actuator and electric systems, we are using OEI condition, which is one engineer system, and to ensure the safe flight. And rather compared to unwinged type, winged type can be much safer, and it can also do the gliding. And as for the lift prop, one of the biggest benefits is that drag minimum propulsion. The lift for lift prop is stopping cruise at drag minimum propulsion. And as for, we are using the Korean battery as well. And also, as for the flight control and the software, it is also locally developed. We see there's much room for growth and expansion in the future. So we are in the process of developing this triple redundancy FC hardware and Korean controller equivalent to DO178C qualification class. And these are the title pages for our system specification or the PIDS. So for the OPPAV. So as I've said, there are new technologies being adopted to OPPAV vehicles, and based on a vast amount of research and study. And we are quickly adopting and introducing new technologies to our model. And I'd like to also share some of our compliance check process. For example, we are carrying out the test to test the material, the characteristics of the materials for the composite materials. And also, we also conduct tests for the static structure. And these are our plans for our compliance check. And at the bottom, we plan to we see that there is no problem for our structure, even if we bring it to the 3 times of the design system for plotter. And we are also taking into consideration the dedicated pad, dedicated vertiport and charging station, and we have completed such vertiport at the end of the last year. And we did the test demonstration at night. And
33m by 33m.
As for the size, the safe area is 33 meter by 33 meters, so it is sufficient for an aerial vehicle with 5 seats. So if there are any companies in Korea that is interested in using this vertiport, you're welcome to do so. And at the bottom of this slide, you can see some pictures of the charging station. And this charging station can also charge aerial vehicle with 5 seats. So generally speaking, this kind of charging station is different from general electric charging station. Since this is for the eVTOL.
다음은 이제 flight control system.
And next, let's move on to the flight control systems. As you can see, I have already told you about the certifications, checks, and
각각 보여주는 부분이고요.
these are how we have analyzed and did the checks for the compliance for FIDS, and also as for the we are also it also includes some descriptions for the reduced flight, and it also we have with Hanwha we have developed a related system. We have developed the hills, and we are doing the integrated test covering hills and others. And as for the subscale test demonstrator, as I've said, our first flight for the subscale test demonstrator was completed in November 2020. This is 44% subscale. So as I've said, the full scale is 7 meters. So the span for this 44% OPPAV is 3.1 meter. And the MTOW is 46 kilogram with battery with 2.1 kilowatt hour battery. We have conducted ground integration tests and also tethered flight test with power crane. We have we have tethered it to a crane. So the first flight was conducted at the Gohung Flight Center. at early November in 2020. You can also check some of our footages on YouTube by typing KARI test demonstrator. And we have done full transition in June last year. I'd like to share a short video clip for full transition. You can decrease the volume. So these were early June last year. We did the autonomous takeoff and landing. This is a point navigation. As for the reduced, this is a reduced OPPAV, so the communication can only reach to 10 kilometers of radius. So we can drive up to, we can fly up to around 50 kilometers. As you can see, we are speeding up. So the rear prop has stopped during cruise. There's no reason why we need to rotate the rear prop while cruising. As you can see, the rear prop and the front prop are arranged differently. So it's coming back. The rear prop, rear propeller are starting to rotate once again. It is auto hovering, and it is also auto making auto landing. So we are currently developing. We were developing the auto landing routine back then. So as you can see, there has been a little bit of time slip, but for the time being, we have completely corrected the time slip problem during the auto landing procedure. So with this, I'd like to wrap up my presentation. Thank you so much for your attention.